Okay, in this problem we have 2 moles of helium, which is a noble gas with the atomic mass unit of 4. It's 4 MUs, and it's at 300 Kelvin, and it is very quickly, here's a big key here, very quickly compressed from 10 to 2 liters. And this is the volume change. New volume is 1/5 the original volume. So what kind of compression is this? By what factors does the pressure change? What factors does the temperature change? And how much work was done by the gas? So the key to this problem is essentially figuring out what kind of compression is this gas undergoing. Okay, so number one, well, I should say, first of all, we know we have 2 moles of helium, and helium is going to act like an ideal gas. It is monatomic. It's very light. You're at 300 Kelvin, so it's going to behave like an ideal gas. We know that the CV is equal to 5 halves. No, let's see. Excuse me, 3 halves. 3 halves R as a monatomic gas, since it has no other active vibrational modes for the heat storage. And the second thing is, what kind of compression? So this is really how you actually figure out this problem. We know the volume changes, but under what conditions? So let's remind ourselves of the kind of conditions you might have. So you've got the compression very quickly, we recall very quickly, from 10 liters to 2 liters. Well, is there a change in pressure? Is it isobaric? Does the pressure stay the same? Well, we really doubt it. If we've compressed 10 to 2 liters, we know that there's going to be a much higher pressure in here. So that is not likely a... well, we'll just cross this out. It's not isobaric. Is it isochoric? We know the volume change is not isochoric. So we're down to these 2 conditions. Is it isothermal or is it adiabatic? And you recall that adiabatic, very specifically, this Q refers to the heat that is transferred between the system, the gas, and the surroundings. Is that transfer of heat, is that 0? I guess maybe a better way of writing this is Q equals 0. Is that heat transfer 0? Well, what about the temperature change? Do we expect the temperature to be the same when you take a gas and you rapidly compress it to a small volume? You probably did this in class, but there's no way this temperature will be the same. It's going to get very hot when you compress it like this. This is actually sort of the fundamental of the first, this is the second stroke of a 4-stroke engine. You compress the gas, it heats up, then you combust it. So it turns out it is an adiabatic that very quickly eliminates the time required for the heat transfer, dq dt. So small, so you do not get a heat loss here. So we have adiabatic conditions. So what that means is then it's a particular set of equations. We know that under adiabatic conditions that again, of an ideal gas, the equations that apply are the ones where we have pressure times volume to the gamma, where gamma equals the ratio of the heat capacities, the constant pressure to the constant volume. This is a constant. So, and we also know that for an ideal gas, the heat capacity equals CV plus R. I'll show you where these are on the equation sheet. Okay, so here's the equation sheet, and if we scroll down here, here we see that here's one equation for an ideal gas here. This work equals P delta V, and you've put the ideal gas equation in this integran and integrated to get this value here. Here's another ideal, this is a equation for adiabatic work. The work is 1 over gamma minus 1 times these different pressures. Now, honestly, I had to look this up. I didn't know this off the top of my head. Of course, I'm imagining that when people are studying for a test, they would, if this were a problem set for the test, they would be looking these sorts of things up. So here is some of the equations. The heat capacity over here. For an ideal gas, and PV to the gamma is a constant. These are all relevant to ideal gases. We also know that under adiabatic conditions, this change in internal energy is equal to Q plus, well, actually this is always true, but this Q is 0. So this is just equal to the work, the delta E. Of course, we don't know the work, so we can't start there to do the equations. So to solve this problem. So let's go over to the original question, which was by what factor does the pressure change? Well, let's see. I'm going to have to work this out. So we know that PV to the gamma equals P1V2 to the gamma equals P1V1 to the gamma, P2V2 to the gamma. Now, we also know that PV equals nRT. So knowing, let's see, we can actually solve for the original P1 because can we solve for that? We know 300, we have 300 here, we have 2 moles here. No, we're a little stuck here. We're just going to need to get the relationship. So let's do this put in place of P1 that P is equal to nRT 1 over V. We'll put that in place here. And let's see, gamma equals Cp over Cv. We know that Cp equals Cv plus R. So let's divide by Cv. Cp over Cv equals 1 plus R over Cv. We know that Cv is 3/2 R. So this is just 1 plus R over 3/2 R, or 1 plus 3/2 under there, 2/3, or 1, which is 1/3, 5/3. Is that right? 1 plus 5/3 equals Cp over Cv equals gamma. So P to P naught. So P to P naught. Let's go P1. Oops, I'm sorry. I'm going to solve for P2. P2 equals, it's late here, and so I get a little bit kind of groggy when it's late. P2 equals P1 times V1 to the gamma over V2 to the gamma, or it equals P1 times V1 over V2 to the gamma exponent. Okay, I'm going to rewrite this. Equals P1 times V naught over 1/5 V naught to the 5/2, 5/3 power, 5/3 power, which is equal to P1 times 5 to the 5/3 power. It's getting kind of messy here. Let me write it down here. So P2 equals P1 times 5, I'll do it this way, the cubed root of 5 to the 5th. Holy Moses. So that is equal to, let's pull one of the 5s out. Does that work? 5 times P1 times the cubed root of 25. So that what I did, it was 5 to the 5th. It was 5 times 5 times 5 times 5 times 5. I took the cubed root of that. And I said it's just equal to the cubed root of 5 to the 3rd times the cubed root of 5 squared. So this is, what's the cubed root of 25? 4 times 4. It's 3 times 3 times 2 times 2 is 4. It's somewhere between 2 and 3, right? Somewhere between 2 and 3. 3 times 3 is 9 times 3 is 27. Let's call it 3. Let's call it 3. So it's about equal to 5 times 3 times P1. So P2 is about 15 times P0. All right, it's an estimate.